So, I want to break the regular format a little bit and do something different. I want to put us in the shoes of a digital engineer that's trying to invent something new and maybe just think of what that process might be. So, let's say that I don't want to use phones, um, and I don't want to use the internet, and no email, and anything like that. I just want to go back to Morse code, right? So that's on off, d d d d d d, long shorts, whatever. Um, and I want to be able to talk to my mom, and my brother also wants to be able to talk to my mom. And I can only have one wire going to my mom, meaning she can't have a wire for both of us because that's just the world that we live in, or at least this problem lives in. So I need to have some sort of system like this. I'm going to say we've got some sort of box. Right now, this is kind of a black box. I don't know what's in there. It's just kind of there for me to kind of imagine what might be going on. And so here's my signal. And here's my brother's signal. And so these are our ins, and this is our output to mom. So, as it turns out, if me and my brother were to send signals at the same time, say I sent a 1 and he sent a 0, uh, that would actually create a short circuit because what this really is 5 volts and this is ground. And so it would create a short circuit and something would light on fire, and I really don't want to burn my parents' house down. So we can't just have some sort of direct connection, meaning that we've kind of got to use our knowledge of digital logic to solve this problem. And so maybe we want to give my mom the ability to select who she wants to listen to, meaning she wants to listen to me or she wants to listen to my brother. And so that means that she's got this output, but she also has her own input where she can select who she's listening to, me or my brother. So let's just call this our select signal, right? And now let's kind of make a truth table here. Um, so we could do a regular truth table where we know that my value could be 1 or 0, my brother's value could be 1 and 0, and the select value could be 1 and 0, in which case we'd have a 3-bit truth table where we'd have 8 rows. And we could do that, and it would work out. But I'm going to kind of abbreviate here and just do this. If, we'll say, this is our select value, and this is our out value. So if select is a 0, then we want the signal to be my signal, whatever this input is. If it is a 1, then we want it to be whatever this signal is, or Mike. So this is kind of our pseudo truth table, you could call it. Let's go from this to a Carnot map, actually. So we know it's going to be 3 variables, and so maybe it would have been helpful for me to go through and draw the entire truth table, but I'm going to kind of make a little bit of a logical leap from here to the Carnot map. And so it looks like I've got 2 S variables and 2 M variables, which is a little annoying. Maybe let's change this select to control, right? This is also a control input. So we'll just call it C. So that means we'll call this C as well, just to make things a little bit simpler here. So we're going to have S, M. So this is my signal. This is my brother's signal. And then we're going to have our control here. And now we're just going to label this like normal. It's always the same. 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Now, we said that if the control is 0, it's going to be whatever value S is. And so remember that this first value listed here, right? This is the first one. M is the second one. And it's that wave, the whole table. So that means if C is 0, whatever S is for that cell is what our output is. So that means here we've got S is a 0. And then here we've got S is a 0. And then here we've got 1 and 1. Now let's do this next one here. So now we've got our control is a 1. So we're going to look at the M signal, or the second signal here. So here, M is a 0. M is a 1. M is a 1. And M's a 0 there. And now our last step is to just circle our implicants. So we've got here and here. And hopefully at this point you should notice, hey, there's a static hazard there. And if we were trying to have this be super error-free, then we could put an implicant connecting those. But in this case, I'm not going to do that. Now, we're gonna actually change this now to out, right? This is just our out signal. So we're going to say out equals, and so it's staying constant in this implicant here. Well, it looks like S is a constant 1. And C is a constant 0. Or, and then here it looks like M is a constant 1 and C is a 1. So this is our function that is describing technically what we want to happen in this black box, right? So this is just 2 AND gates, an OR gate, and a NOT gate. So this device that I'm kind of designing in my head, or more properly put on the computer right now, is it actually exists, and it's very highly useful. In fact, it's my favorite digital logic circuit. That's why I always like to kind of explain it as if I invented it, so maybe you'll think I'm smart, but I'm not really. I did not invent the multiplexer. So there I said it. The name of this device is the multiplexer. So multiplexers are very useful because they allow you to select multiple signals, or select from multiple signals. We could actually scale this up to have multiple multiplexers connected, such that we could now select from 4 inputs or 8 inputs or 16. So they're very useful devices. You see them a lot in communication systems. They're even used in FPGAs, right? In the previous video, when I kind of talked about the concept of an FPGA, we had to have something that I just kind of hand waved, but we had something that was setting our connections between our logic elements, and so a multiplexer can be used to do that. Actually, later we'll see that multiplexers can be used to implement full Boolean expressions. Like, you don't even need any gates. You can just do stuff with just multiplexers. To me, they're kind of the miracle device because you can do so much stuff with them.